Good day, I'm Don Tuite for Engineering TV. Today we're talking to David Reusch of Efficient Power Conversion, EPC, about gallium nitride and how to get the most benefit from the efficiencies that gallium nitride provides. David, can you elaborate on that?
Well, first, thank you, Don. As power engineers, what we're always trying to do is increase power density, and that means pushing more power in an ever-decreasing board space. And to do that, you need to improve your performance of your power converters. And in particular, you'll need a better switching technology. And gallium nitride has a number of material advantages over its predecessor silicon, and we'll talk a little bit about how you can improve not only your electrical in-circuit performance, but also your thermal performance. And that's going to give you better overall performance in your designs and allow engineers to get higher power density to continue to meet the ever-growing demands for higher density and higher performance.
Okay, so what have we got for show and tell here?
So what we have here is essentially we've got some standard MOSFET technology packaged, and this is an S308 or LF pack. And this is what MOSFETs have been using in various forms for a variety of years. As the push for power density, better electrical and better thermal performance, MOSFETs have tried to improve their packaging, improve the ways that they can get better electrical as well as thermal performance. And something like this is a double-sided cooling MOSFET package. And what we have are eGaN FETs. As you can see, first it's very small and it has a much lower on resistance, and that has to do with the advantages of the gallium nitride. But also with our chip scale packaging, we can get much better thermal performance, true double-sided cooling. And that's going to help the user extract more power from their design.
Does the area matter? Because you've got a smaller area there.
Well, and that's true. So when you look at thermal resistance or thermal impedance, as you continue to make these chips smaller, you have less area to get the heat out. And that's why the thermal efficiency of the package just becomes that much more important. So when you look at the graph that we have here, when you look at the y-axis, you'll have the thermal impedance. And on the x-axis, we look at die size. And what you can see is you make a die smaller, the thermal impedance will go up. When you look at the ability to deliver heat from the device to the PC board, using that as a cooling path, you see that it's pretty consistent with technologies. For the different MOSFET packages and with GaN, it's pretty a consistent trend. But looking at junction to case, or taking heat out of the backside, the alternate path, you can see that the eGaN FET has significant advantage. And that has to do with the chip scale packaging. When you look at a MOSFET device, there's a lot of layers built in. Each of those layers add inductance, they add resistance, they add cost, they lower reliability, and they significantly impede the thermal flow. So the devices are not going to be as thermally effective.
David, these thermal advantages, what can a user actually expect?
So what we did, Don, that's a valid question, is what we did is, again, we built a variety of equivalent in-circuit test comparisons. We used the same size board, the same number of copper layers, same copper weight, same vias. We wanted to keep it as equivalent as possible. And then when you run the gallium nitride devices, besides the best state-of-the-art silicon MOSFETs in the standard packaging, as well as advanced double-sided cooling MOSFET packages, you can see a significant advantage with eGaN FETs. Without heat sinking or active cooling, we saw around a 40% increase in output power. And as we can see by our boards itself, the device is already smaller. So we're talking about shrinking the size and increasing the power capability. When you look at things like adding heat sinks or airflow, the double-sided cooling really shines and our advantage just grows. We have around a 50% increase in capable output power. And that's from a combination of two things. It's better electrical performance and it's better thermal performance.
Can you go into a little more depth about what a designer has to do to make sure that he or she is using the package correctly?
So with GaN, there are some nuances to design, and we have a variety of materials. We have some textbooks talking about the basics, and our website at epc-co.com has a number of white papers and app notes telling and educating users how to properly use these devices, which again are much faster than their silicon predecessors, and do offer a slightly more challenging design. But with high performance, new approaches need to be taken, and we are supplying our users and the engineers the tools to be successful designing these parts into their boards.
All right, and one more time, where do people go to get that extra information?
So you can go to our website, epc-co.com. We have a number of white papers, application notes, as well as demo boards, which have various circuit examples, and users can take these and evaluate, learn, get to use their devices, and then it'll help them design them into their boards in products going forward.
David, thank you.
Thank you, Don.